Yes, good morning, and thank you for coming to hear about one of my favorite topics. It was only after I had submitted the final version of the slides that I had noticed that I had forgotten to mention what RO4000 materials are. Let's say, this is Rogers commercial high-frequency circuit substrate. It's based on fused silica-filled hydrocarbon resin, glass reinforced. It processes quite similar to FR4, but has excellent high-frequency properties. The RO4003 has a loss at X band of about 0027, and the flame retardant version, RO4350, is a loss of about 0035, and they're very stable materials with very low z-axis CTE and an excellent temperature coefficient and dielectric constant. What I'm going to tell you today is that conductor roughness causes a much larger increase in insertion loss than what's predicted by the textbook correlations, particularly at higher frequencies, and also that unexpectedly, conductor roughness causes an increase in the phase constant, or essentially the effective dielectric constant, and also increases dispersion. And the increase in conductor loss, phase constant, and dispersion are larger with thinner circuit laminates. And for all of these reasons, Rogers has newly introduced the RO4000 Low Pro laminates, which has a proprietary foil treatment that has allowed us to achieve good peel strength with low profile copper. And RO4000 Low Pro laminate should be specified whenever the best high frequency electrical performance is required in a commercial thermoset material. First a little background on copper foil technologies. Electrodeposited foil, like the name implies, is formed by electrodeposition on a polished rotating stainless steel or titanium drum from a copper sulfate solution. The manufacturer of the foil adjusts the chemistry and current density to control the roughness on the bath side of the foil, while the and the smooth profile is controlled by the surface of the drum. Also, as the name implies, rolled copper foil is made simply by rolling from they start remarkably with about a foot-thick billet and put it through a series of rolling machines and get it down to between 15 and 70 microns. Additional foil treatments are plated by the foil manufacturer to improve and preserve adhesion to the dielectric. The standard ED foils are treated on the rough or bath side of the foil. The rolled foils are originally smooth on both sides, and one side is generally plated with the treatment, and that has a lower surface profile and a different treatment structure than standard ED foils. And more recently, foil suppliers are manufacturing reverse-treated ED foils that are treated on the smooth or the drum side and can be very similar in electrical properties to rolled foil. Here's SEM photographs about 2500x of the two extremes of copper surface profile. On the right is rolled foil, which is about 0.4 micron RMS roughness, and you can see it kind of looks like broccoli growing in the Imperial Valley. And on the left is about the highest profile ED foil that you'd see in circuit substrates, which kind of looks like the sequoias growing in the Sierra Mountains. If you're attending IMS, I'm not going to be able to tell you anything about skin depth that you don't already know. The only reason I put up this slide is to remind you that at frequencies of about 1 gigahertz, the skin depth becomes less than the typical roughness value for laminate copper foils. The fact that conductors with rough surfaces increase the loss of high-frequency devices was certainly known since the 1930s. The first analysis that we're aware of is a 1949 paper from Bell Labs in which Sam Morgan numerically solved Maxwell's equations for the effective rough conductors. And he looked both at, it was a two-dimensional model with both triangular and square roughness patterns, and they both gave quite similar results. And essentially what happens when the skin depth is about the same or less than roughness, the roughness increases the conductor loss compared to a smooth conductor. In years since, the This numerically calculated data have been fit to the following function, and I guess this is most widely publicized in 1980 paper on by Hammerstead and Jensen on microstrip circuit design. The way this works is the alpha conductor is what you would normally calculate for the for the attenuation factor for the conductor if it's perfectly smooth, and then the argument on the right is the arctan of the ratio of the RMS roughness to the skin depth. So what happens with the arctan? If you're below a certain value of the ratio of roughness to skin depth, essentially the arctan is 0. Then you're multiplying the alpha of the conductor just by the value of 1. And when the value of the roughness to the skin depth becomes large, the arctan approaches pi over 2, multiply that by 2 over pi, and you essentially double the conductor roughness compared to the smooth conductor. Yeah, this is a graph. Here what we're plotting is the conductor attenuation factor against the frequency. And with the conductor roughness as a parameter, you can see it as with rough foil, like the 2.5 micron RMS material, you are essentially approaching doubling the conductor loss, even as frequencies as low as 1 gigahertz. And you can see with very smooth foils, such as the 0.4 micron, there's like a minimal effect until you're well beyond X-band. And actually, if you look at what's been normal high-frequency circuit substrate thicknesses and frequencies in the past, these simple equations really seem to be a reasonable representation of reality. And on the next slide, we've got just insertion loss data that we measured on a PTFE laminate. They're at 0.20 thick. And this was over, with a wide range of different, different conductor profiles, and you can see that that they fit within the extremes of what you calculate using the Hammerstead and Jensen model for both smooth and rough conductors. However, if you look at thinner dielectrics and higher frequencies, it'll become evident that roughness can cause more than a factor of 2 increase in conductor loss. In the last few years, several papers have been published on this phenomenon. However, the Hammerstead and Jensen Morgan correlation is not too misleading, up to about 10 gigahertz. Okay, remember now the insertion loss is made up of 2 independent contributions, dielectric loss and conductor loss. The dielectric loss is a function of the tan delta, or dissipation factor of the material, and increases linearly with frequency. The conductor loss is a function of the conductivity and increases the square root of frequency. And also for a 50 ohm line, conductor loss increases as material becomes thinner since the trace width decreases. If one is considering low dissipation factor tan delta materials, conductor loss can be a surprisingly large fraction of the total insertion loss. On this next slide, I've calculated the total insertion loss and the relative contributions of the conductor and dielectric. This is essentially modeled for an RO4000 with a dielectric constant of about 3.66 and dissipation factor of 0035, and with an 8 mil ground-to-ground spacing. So you can see down in the low gigahertz range, it's essentially 95% conductor loss, and even up as high as 50 gigahertz in this circuit, it's still 75% of the total insertion loss is due to the conductor. Okay, now how this all fits in with 4000 is these, all high-performance thermoset hydrocarbon materials are apolar, if you were paying attention in freshman chemistry, and it's this low polarity of the resin that makes them have the low dielectric constant and low dissipation factor. The downside of this is that low polarity resins do not naturally exhibit good adhesion to metals, so historically manufacturers of these materials have used high profile copper foil to achieve good copper peel strengths. So after years of work, one of my colleagues, far more brilliant than I in Rogers R&D, has developed a copper foil treatment that allows us to use low profile reverse treated ED foil without deleterious effects on other properties of the RO4000 hydrocarbon substrates. So now we'll present some of the insertion loss and phase constant data. Our test procedure is to conduct a full 2-port calibration over the desired range up to the cable lens. We're measuring the S21 and phase angle of two different lengths of 50 ohm microstrip transmission lines. And then to gauge out the small effect of the fixture, we subtract the measured values and divide by the length difference. What we have plotted here is the insertion loss in dB per inch versus frequency on RO4350B, a 20 mil thick laminate with both the standard high profile and the new low pro foil. And you can see at this thickness, there's about a 0.4 dB improvement simply by going to smoother foil. See, as you go to thinner laminates, this is 6.6 mil. You can see that the difference in insertion loss becomes more pronounced. And on 4 mil laminate, there's nearly a 0.7 dB per inch difference at 25 gigahertz, again, simply by using the low pro foil. And on the last slide, we'll see as you go to higher frequencies out to 50 gigahertz, we're even looking at, again, at a 1.5 dB per inch difference for the low pro foil. A more surprising result is that the phase constant, or essentially the effective decay, can be substantially affected by the copper foil profile. And what has the height with the high profile foil, the effective dielectric constant increases as laminate thickness decreases, and with the low profile foil, the effective decay actually decreases a little as laminate thickness decreases. So what I have plotted here is the the back calculated dielectric constant of the substrate based on having measured the K effective of the microstrip line by as derived from phase length. You can the solid the solid symbols are for the RO4003 and 4350 with the standard high profile foil. And you can see as you go from 020 laminate to thinner laminates, the effective dielectric constant of the substrate increases from about 3.65 to 4. And with the low profile foil, it decreases from about 3.55 to about 3.4. So remember, dispersion is a change in effective dielectric constant or propagation constant with frequency. More dispersion leads to pulse broadening and degrades eye diagrams in digital systems. And rough copper foil substantially increases dispersion as the substrate thickness decreases. And what I've got plotted here is dispersion, which is the difference, or I've defined for this slide, as the difference between the dielectric constant at 50 gigahertz and at 8 gigahertz. And again, plotted against laminate thickness. You can see for the solid symbols for the standard foil that as you go to thinner laminates, the dispersion is about 0.08, while as the highest value that you see for the smooth foil is about 0.04, or half that of the rough foil. So what's causing these effects? Because all three unexpected effects, both the higher loss, dielectric constant, and dispersion, are simultaneously quantitatively modeled in Sonnet high-frequency electromagnetic software by an increase in the surface impedance caused by the roughness. And if you'd like to hear more technical details, we'll be presenting them tomorrow in session WE4B3 at 410 in room 206AB. So just in conclusion, remember that conductor loss can be the major component of insertion loss. High profile foil can substantially increase conductor loss to a greater extent than previously thought. High foil profile also increases the propagation constant and the calculated apparent substrate dielectric constant. And higher profile foil also increases dispersion. And one last important conclusion, you should use Rogers RO4000 low pro laminates to substantially decrease the insertion loss, phase constant, and dispersion in commercial applications. And that brings me to the end.
Let's thank our speaker, and I'm going to open up the I'm going to open up this presentation to questions. If you have questions, please come up to the mic and speak right into the mic.
How are you? Thank you. Just a question on cost difference. I mean, I don't want to price, but how much more or less between the materials?
I'm the R&D guy, so they're going to give me that kind of
a
information, but our product manager is right there. I say, like this.
Well, I'm saying, you know, why wouldn't the 4000 low pro line just replace the the other old line? I mean, it must be a cost issue then.
Please come up and you can speak to that question. That's fine.
Yes, yeah.
We're at open dialogue here.
At low volumes, we offer low profile for roughly $1.20 a square foot. Obviously, with higher volumes, it can get discounted from there. It's an adder. Actually, the low profile foil has a proprietary resin that's added to that's treated to the reverse treated copper, and so obviously we have to recover our costs and make a little money in that.
Thank you, Dr. Horn. This was a very good, I think, very complete characterization of the surface roughness on both the loss and dielectric constant deviations from the textbook, as you pointed out in your presentation. I really appreciate this kind of very practical and detailed characterization, because this is one of the things that